Dear students, today we will learn an expression for Young's modulus of a single cantilever. Let us consider a single cantilever, which is nothing but a beam which is fixed at one end and it is being loaded at the other end. Such an beam we call it as single cantilever. Let L is the length of the beam Mn. L is the length of the beam Mn, which is fixed at the end M and it is being loaded at the end N. And due to the stress that is being applied at the free end, the depression at the free end is Y naught. The depression that is produced is Y naught. Now let us consider any arbitrary point P which is at a distance of x from the fixed end so that its distance from the loaded end will be L minus x, and the depression produced at the point P is y. You can notice from the diagram it is small y, and as we move near to the fixed end, we can observe that the depression is being decreased, and finally at the end M the depression is 0. So we can write at x is equal to 0, depression y is equal to 0. So this will help us further derivation. Now we know that the bending moment acting on the beam is given by the general formula force into perpendicular distance. That is the expression for moment of a force or torque. So in this case, the force is W. W is the load that we have suspended, and the perpendicular distance is the distance of the point P from the loaded end. So that is P is at a distance of L minus x. So perpendicular distance we have taken as L minus x. So the bending moment can be written as W into L minus x using the general formula. We know that the bending moment of a beam is given by another formula, y by r into Ig. Y by r into Ig, where y is Young's modulus, Ig is geometrical moment of inertia, and r is the radius of the neutral surface. So by equating this, the bending moment, we can write y by r into Ig is equal to W into L minus x. So by retaining 1 by r on the left hand side, we can write W by y into Ig into, in the numerator we are having L minus x. Let us correct as equation number 1. It can be shown that 1 by r is equal to d square y by dx square. D square y by dx square, where dy by dx is the tangent to the curved beam drawn at any point. Equating equation 2 and 3, equating equation, so we call this as equation number 2. Equating equations 1 and 2, we can write d square y by dx square is equal to W by W by Y into Ig into L minus X. Correct as equation number 3. Now the left hand side d square y by dx square can be split and written can be written as d by dx into dy by dx, which is, if you multiply it, we are going to get d square y by dx square is equal to w by y into ig into L minus x. Now take the term dx. By taking the term dx to the right hand side, so this can be written as d of dy by dx is equal to w by y into ig L minus x dx. Dx we have shifted to the right hand side. And further, taking dx to the terms inside the bracket, it will become d into dy by dx w by y into ig L dx minus x dx. Now integrate this. Upon integration of the above, integrating this with respect to x, integrating, the left hand side will be dy by dx is equal to w by y into ig. Integration of dx is x and integration of x dx is x square by 2 plus integration constant c1. We can observe from the diagram that the tangent drawn at any point, is nothing but dy by dx, right? So the tangent to the curve at any point is dy by dx, and we can see here the dy by dx keeps decreases, and at the fixed end, that is at x is equal to 0, there is no bending of the beam, hence the tangent dy by dx will also become equal to 0. So by using this condition, that is dy by dx is equal to 0, dy by dx is equal to 0 at x is equal to 0, we can evaluate c1, substitute this, so we will get, it leads to c1 is equal to 0. So using the value of c1, we can write dy by dx is equal to w by capital Y, that is the Young's modulus, into ig L x minus x square by 2. Correct as question number 4. Integrate this equation 4 once again. On integrating once again, the above equation, so we will get, so let us rewrite this, dy w y into ig L x dx minus x square by 2 dx. Now integrate. Integration of dy is nothing but y, that is small y, that is nothing but depression, w by capital Y, that is Young's modulus. So you need to understand what is small y and what is capital Y. Small y is the depression, capital Y is Young's modulus. And integration of x dx is nothing but x square by 2, whereas integration of x square is nothing but x cube by 3, x cube by 3 plus integration constant c2. So this can be written as y, small y is equal to w by capital Y into ig L x square by 2 minus x cube by 6 plus c2. So using the condition that depression is 0 at the fixed end, we can see that we already told that depression will be 0 at the fixed end, since the beam do not bend at the fixed end, right? Y is equal to 0 at x is equal to 0. So by using this, we can find out the integration constant c2, and it turned out to be 0. So using the value of c2, we can write y is equal to w by capital Y into ig L x square by 2 minus x cube by 6. Now, on the right hand side, within the bracket, we can take LCM for this and simplify this. So we can write it as w by y into ig. So it will be 12 it will be 6 L x square minus 2x cube. And now by substituting x is equal to L, right? At x is equal to L, that means the point P, if we shift to the free end, then the depression can be written as y can be written as y naught. Y can be written as y naught. Using this, the above equation becomes y. In place of y, we should substitute y naught, and in place of x, we should substitute L. So it will be w by y into ig 6 L into L square, that will become 6L cube minus 2L cube. In place of x, we are substituting 2L cube by 12. So it gives us 6L cube minus 2L cube is 4L cube. So 4 I'll write here 4W into L cube by Y into IG by, that is IG into 12. This is left hand side is Y naught. Now we want the expression for Y. Let us move this capital Y to the left hand side, and also we know that the value of IG for rectangular beams, it is BD cube by 12. BD cube by 12, and also we can write W is equal to M into G. So using this, we can write Young's modulus as Y is equal to 4 into mg into L cube divided by y naught. Ig is BD cube by 12, BD cube by 12, so into 12. So this 12 and this 12, it cancels. So the final expression for Young's modulus of a single cantilever becomes 4 mg L cube divided by BD cube into y naught. So this is the expression for Young's modulus of single cantilever. I hope you understood the Young's models of single cantilever. Thank you for watching.